Welcome. In this session in linear data analysis, we'll explore orthogonal vectors and orthogonal spaces. Let's begin by recalling the definition of orthogonal vectors. So, if we have two vectors that are in the same space, and vectors u and v are orthogonal, and we define that, or we intend that to be, that the dot product of u and v is 0, or we could write that as u transpose v equals 0. And when we have a basis, so if we have an entire basis of vectors, and we call them all u, and we'll index them as I, we'll say that the basis is an orthogonal basis. And what that means is that if I and j are distinct numbers, then the dot product of the ith basis vector and the jth basis vector has to be equal to 0. And so this is a special kind of basis. We don't know how to calculate this kind of basis yet. This will take us quite a few sessions to get to the calculation. But this is a very special basis, and it's one that we want, if we can possibly get it, for numerical accuracy and for a number of other useful properties that we'll explore as we continue in linear data analysis. A related idea is an orthonormal basis, or an orthonormal set of vectors. And these have the property that they are orthogonal, and the additional property is that the dot product of any vector with itself is 1. Let's go through a few examples and explore whether they're orthogonal or orthonormal. Suppose that we're given some size 3 vectors. Suppose that the first one is 1, 0, 0, and the second in our set is 0, 0, 1. And we can see immediately that the dot product of these is 0, and the dot product of this with itself is 1, and this with itself is 1. So this is an orthonormal basis. Suppose that we're given vectors 1, 0, minus 1. So that's the first one of our set. And suppose that we're given 1, 0, 1. And we can calculate the dot product as 1 plus 0 plus minus 1 is 0. So these are orthogonal, but they're not orthonormal because the dot product of this with itself is 1 plus 0 plus 1 is 2, and similarly 1 plus 0 plus 1 is 2. So I would have to make these into an orthonormal basis. I would preserve these vectors and I would scale them. And I would scale them by their norm. And if the dot product of this is 2, then its norm is the square root of 2. And so I could convert that. Let's use a double arrow to convert it. I could convert this to an orthonormal basis by saying this is 1 over the square root of 2, 0, and minus 1 over the square root of 2 for the first vector. And then I could likewise, the dot product of this with itself is 1 plus 0 plus 1 is 2. Its norm is the square root of 2. Divide it by the square root of the norm, and I get 1 over root 2, 0, 1 over root 2. And we can quickly verify that these have preserved the orthogonality property by taking the dot product of the two vectors. So that would be 1 over root 2 times 1 over root 2 is 1/2. That's 0. And that's minus 1 over root 2 times 1 over root 2 is minus a half. 1/2 minus 1/2 is 0. So these are still orthogonal vectors. And then the dot product of this vector with itself is 1/2 plus 0 plus 1/2 is 1, and likewise 1/2 plus 0 plus 1/2 is 1. So these are an orthonormal basis, these are an orthogonal basis, these are an orthonormal basis. An allied concept is what happens if we have basis vectors for two spaces. So let's consider vector spaces double-barreled U and double-barreled V. And let's suppose that if U is not the zero vector, in vector spaces we're forever having this requirement, by the way. Suppose U is not a zero vector and little u is in big double-barreled U. And suppose that that is true if and only if U is not in the subspace V. Well, if this condition holds, that every vector in U, that every non-zero vector in U is not in V, we would call, so we say that U and V are orthogonal complements. And in the literature, you will see three terms used for these vector spaces. One is they're orthogonal complements, one is they're orthogonal, and one is they're complements. And they all mean the same thing. So the dot product rule is that if we have two vectors, U that is non-zero and V is non-zero, that if little u is in set U and little v is in set V, then we can say that the dot product of U and V is 0. So let's take an example. And suppose that we look at vectors that have 3 entries each. Well, suppose that we say that the set U is the vertical axis or the z-axis. So a U vector is proportional to, that is, it's a scalar multiple of 0, 0, 1. And then what we would say is that a basis for V is the set. So what vectors are guaranteed to be orthogonal to 0, 0, 1? Well, they are the set of vectors that have a 0 in the third entry. And so if we set up a basis that has zeros in the third entry, we're good. So that would be 0, and so now we have to do a little bit of reasoning. How big is this space? How many basis vectors do we need? Well, I can reason this in a couple of ways. Let's use a simple way, and that is if the last entry is 0, then there are 2 entries left to fill in. That's 2 degrees of freedom, and so I must need 2 basis vectors, and this must be a 2D space inside R3 coordinate space. So that means that they have to be like this. Now, there's an infinite number of choices, and the simplest one would be 1, 0, and 0, 1. And you can verify that any multiple of this plus any multiple of this, if we take that, the dot product with u has to be 0, because whatever values we put in here, so if we take W1 times basis vector 1 plus W2 times basis vector 2, and then we take the dot product with u, well, this will be W1 times this will be W1, 0, 0. W2 times this will be 0, W2, 0. The sum will be W1, W2, 0. And when we take the dot product of W1, W2, 0 with u, what we get is the 0, is 0. So this is a simple example, and what that's saying geometrically is that the xy plane is orthogonal to the z-axis. The xy plane is a vector space, the z-axis is a vector space, and these are complementary vector spaces.